Hello, SPH4C, Mr. LaRusso here again. We're on to our next unit, which is energy transfer, work, and power. So let's start off with the concept of energy. Everyone has heard the word energy, of course. It's the commonly used word in English, but what exactly is energy? Well, the definition for energy is the ability to do work. Now, that obviously is not the most inclusive definition of what energy is, but the interesting thing about this is the best definition that we have of what energy is. The truth of the matter is no one actually really knows exactly what energy is made up of, what its fundamental nature is. So we only know energy by what it's able to do. Let me give you an analogy of how, really in the grand scheme of things, how incomplete this definition is. This would be like saying, what is the definition of a car? And the reply would be the ability to go from point A to point B. Now, that is true of what a car does, but that hardly speaks to what actually a car is. We run into the same problem with energy. We actually don't really know what it is, but we know what it does. So we're going to talk about what this ability to do work actually is a little bit later. All right, so now, here are some things that we do know about energy. Energy is transferred from one object to another when work is done. All right? Energy comes in many forms that are all interchangeable. Energy can be stored and later used to do work. Energy is always conserved, meaning it cannot be created or destroyed, and energy is measured in joules. So let's tackle one thing at a time. All right, so as mentioned, energy is the ability to do work. Well, what are some examples of work in the context of physics? Well, for example, let's consider lifting an object, any object, heavy or not. So we have the ground here, and we place this heavy object on the ground. If we just leave it there, it's not going to do anything. It's just going to stay put. However, if we come along, grab it, and we lift it up, we are applying an effort to lift this vertically. This requires us to use our muscles and to get this object to increase in height. Now, what we have done is we have given this object a special kind of energy. In this type of energy is called gravitational potential. So, for example, if we let go of this thing is going to fall and smash back down to the ground. Now, depending on how high this is and how heavy this object is, it can actually do some damage to the ground, which means that it's done some work on it. All right, so now, right now, it doesn't have any ability to fall. By lifting it like this, we have given it some ability to fall. And of course, when we let go, this object is going to start to accelerate and hit the ground at some speed, which is defined by its height. So what we have done is we have taken some of the energy in our body, which is we get from our food calories, because food is another form of, is a type of energy. And we've placed some of that energy that we got from our food into this object. And now when we let go of that object, we can get some of that energy back in terms of speed, which we call kinetic energy. And then, of course, when it smashes into the ground. So every time that there's an energy exchange, the concept of work is being done. Now, what we're going to do is we're going to think of energy like money. Energy behaves like currency in an economy, right? The currency, in ideal terms, the total amount of money in a closed little economic circle is fixed. So let's say, for example, in our classroom, the total amount of money in the classroom is the cumulative wealth of every individual in that room. So let's say we give one person $20. That $20 is a loss for you, but a gain for that other person. But inside the room, the total amount of money stays the same. It's just transferring back and forth, right? And we consider that concept work. And in many ways, when you do work, it actually is a transfer of money when we go to our jobs. But in physics, it's not a transfer of money, but a transfer of energy, which is measured in joules. Next, energy comes in many forms that are interchangeable. So there are basically two categories for that. We have what are called your potential energies, and what we have is your kinetic energies. Potential energies are energy storage spots. It's where we can actually temporarily store our energy for later use. Examples, if we lift this object up and hold it there, right? So let's say we tie it to a string and hold it up there. Right now, what we've done is we've stored this energy. This energy that we put into it is still there, and while it's held up by this rope, it isn't going to do anything. But if we cut this rope, we're going to get that energy back, and then it's going to start to move. So batteries are another example of stored energy. Food, right? When we store food, food is a type of energy. It's in the form of chemical energy. Then the other types are what we call our kinetic energies. And these are the energies associated with things that are moving. So when an object moves from point A to point B, when it has velocity, when it has speed, I should say, it has what we call kinetic energy. So any type of motion is considered of the kinetic variety, and any type of stored energy is considered the potential type. And that's where we talk about this energy can be stored. That refers to our potential energies because it has the potential to cause objects to move later. Now, the next thing, energy is always conserved, meaning that it cannot be created or destroyed. And again, this is the whole idea of the money that circulates in the classroom. If you give somebody $20 in the classroom, the total amount of money in the classroom stays the same. It just means you're moving it from one person to another. It's just this contained flow. As it turns out, when this law applies for the entire universe, which means the total energy in the universe right now is the same as it was yesterday, as it's the same as it was last month, last year, last century, last millennia, going all the way back to creation, back at the Big Bang at 13.7 billion years ago. The total energy in the universe is a constant amount. The entire time the universe has existed, it's just energy exchanges from one object to another and going into different forms. So what we got is what we got. We can't get more energy. We can't get rid of that energy. The total energy in the universe is the same. What's happening though, it's just constantly being transferred from one object to another. So the energy is flowing throughout the universe and changing in different forms, but the actual total amount is the same. And finally, the units for energy is the joule. Now, the joule is named after an English, believe it or not, a brewmaster who happened to also be an accomplished scientist. But this individual was actually most interested in perfecting his brewing techniques. And he invented at the time the most accurate thermometer. And he noticed, based on some of his experiments, some strange things happening. For example, when he was stirring the wort of beer, he noticed that after doing some stirring, the temperature increased just by stirring the mixture. And that's when he started coming up with some of these ideas. So energy comes in many forms. Energy can be transferred from one form to another when work is done. So the unit for energy is joules. The other unit that you're familiar with, right, is something called the calorie. Now, one little calorie, small c calorie, is equal to 4.184 joules. But the confusing thing about calories is sometimes it's spelled with a capital C. Little capital C means a kilocalorie, which is equal to 4,184 joules. Just to give you some context, the average person needs roughly about 2,000 big C calories a day just to get by. That obviously varies from individual to individual. Smaller humans require less, larger humans require more, but on average, it's about 2,000 of these big C calories. So 2,000 big C calories or 2 million little calories per day. So for us to live requires a lot of energy input. And where we get that energy from is from food. And we'll talk a little bit more about where food gets its energy from. All right, so now let's go into those category types again. We have potential energies and we have kinetic energies. So potential energy is the stored energy due to an object's state. Yeah, it's called potential energy because the stored energy has the potential to do work later. So it's just stored. So examples, chemical potential energy. So this is energy stored within the molecules of a substance. Examples, food, fuel like gasoline. The energy can be released later and be harnessed to do work. So obviously gasoline, we can burn it. Food, we can digest it. Dynamite, we can blow things up, right? All of these potential energies are designed to feed or fuel kinetic energies later. Nuclear energy. Now, This is the energy stored within the nucleus of an atom. And with nuclear energy, a tremendous amount of energy is released when the nucleus of the atom is split or fused. So when the atom is split, we call that nuclear fission. And that's how all our nuclear power plants, or more frighteningly, nuclear weapons operate. They actually break a uranium atom into two pieces, well, more than two pieces, but basically two chunks of stuff plus a few extra little pieces that fly off. And a ton of energy is consumed, released, I should say, during one of those events. So a nuclear power plant uses the splitting of an atom and the heat generated from that to make electricity. The sun uses a different process. Instead of nuclear fission as in to break apart, as in a fissure, it uses nuclear fusion. And nuclear fusion means when you fuse two atoms together to make a new one. So the sun takes two hydrogen atoms, forces them together to produce a helium atom. Gravitational potential energy. This is the stored energy of an object due to its position above a large celestial body like the Earth or the sun. So basically, how high off the ground and how heavy an object is determines how much gravitational potential energy it is. Energy released from falling objects can do work upon impact. So like example, a pile driver. A pile driver is basically a massive chunk of metal smashing down onto telephone pole sized piles. Hydroelectric power plants use gravity to run them as well. Water runs downhill. The water that flows downhill turns the turbines, and we turn those into electricity. Elastic potential. Elastic potential energy is stored by bending, stretching, or compressing elastic materials. So like a slingshot or a shock absorber, these are all examples of elastic potential energy. And these are temporary deformations of the elastic material. And what I mean by temporary deformation is you bend the material, but it bends back to normal, to its initial state. So slingshots, spring motors, even a slinky. Electric potential energy. This is the stored energy of charged objects due to their relative position and charge. So an example is when you're a little kid, you took a balloon and you rubbed it against your head and the balloon stuck to a wall. That's a buildup of static charge, and that's a form of electric potential energy. In electronics, things like capacitors are an example of electric potential energy. They sort of store the energy temporarily. Batteries, something very, very similar. Power supplies, these are all examples of electric potential energy, where the energy is stored based on how many extra, as in surplus or deficit of electrons that we have. Magnetic potential energy, similar to electrical potential energy, except we're talking about using magnetic fields. So you can actually store energy in magnetic fields by getting two magnets, their north poles pushed together, or separating a north and a south pole. Those are all forms of potential type of energies. Kinetic energy. Kinetic energy is the energy associated with motion. So anytime you have any type of motion whatsoever, moving from point A to point B, that is considered kinetic energy. Kinetic coming from the Greek word kinesis, which means, to move. So bulk kinetic energy is the energy due to the motion of an entire object. So when you throw a projectile, so if we take a ball and we throw that ball across that motion of that object, the entire motion as it moves, we call that bulk kinetic energy. The entire thing en masse is moving from point A to point B. Now, and the reason why we say that is because every object is filled with smaller sub-objects, like atoms specifically. So when we talk about bulk kinetic energy, we're talking about what the motion of the collective of every atom inside this single thing. Basically, imagine being on a cruise ship. The bulk kinetic energy would be represented not by the individual motions of humans walking on the ship itself, but the entire ship and its contents moving from one port to another. Sound. Sound is energy transmitted from molecule to molecule within a medium. What do I mean by a medium? Things where the waves can actually travel through. So for example, we live on a surface of a planet that has an atmosphere that is made mostly up of nitrogen and oxygen and other elements such as carbon dioxide, molecules, I should say, such as carbon dioxide and other elements, oh my goodness, as well as other molecules as well. But that's a medium. Water is a medium. Concrete can be a medium. And sound is the transmission of these pressure waves from point A to point B. So for example, as you are listening to me, the sound of my voice is moving the air near my mouth, which then these vibrations are being picked up by my microphone. This microphone then encodes that information digitally, sends it to you, you play it back, and through either your headphones or the speaker on your phone, the air gets vibrated and you hear those energy waves, the original ones that I spoke into. They come through your speakers, or if you're listening to me in real life, directly from my vocal cords. If you like to play music, your guitar amps. These are all examples of sound. Now, thermal energy is the energy of an object due to the random motion of the molecules within the substance. So that basically means this. If you have, let's make a little H2O. So what we're talking about in terms of thermal energy is we're talking about the actual vibration of the atom back and forth like this. Also the vibration back and forth between these two bonds, and the vibration here and the vibration there. So the whole hydrogen, the whole water molecule is actually vibrating in multiple ways. So it's these bonds are vibrating up and down. This bond is operating up and down. These bonds are moving in and out, and the actual whole molecule itself is vibrating back and forth. And that's all related to thermal, not to be confused with bulk kinetic energy. Bulk kinetic energy is how the whole thing operates in one go. Thermokinetic energy has to do with the behavior of the individual atoms themselves. Radiant. Okay, notice the root word of radiant. The root word of radiant is radii. That's where we get things like radius, radio, radiation, radial. These are all examples of things moving along circular lines, specifically along radial lines of a circle. So when the sun gives a heat to the earth, it gives it off in the forms of radiation. Well, if you look at how people always sketch the sun, they always draw the sun like this, which is conceptually very accurate because these actually represent the arrows of the direction of the energy that's coming from the sun, which is going in every direction at once towards us. So this would be the visible light that we see, the infrared that heats the earth, the ultraviolet that gives you a suntan, the X-rays that also bombard the earth that can be dangerous, and gamma particles as well. These are all examples of radiant energy, and they move along radial lines of a big, big sphere. And then electric. Electric energy, this is the energy of actually flow of moving charges. And so this is associated with moving charges. This is why your power supplies get hot, right? Your electric stove, when you turn it on, this moving of these electrons cause the actual elements to warm up. So any electricity or charges that are moving, that's considered kinetic type energy. And as mentioned earlier, energy transfers means that energy can be converted from one form to another. So let's consider some big ideas. I mentioned lifting this block over here up. Well, in order to lift that block up, you need to exist. For you to exist, you need several things. One of them, importantly, is food. Okay, well, where does our food get the energy from? Well, let's take a look. If we consider our sun, the sun is a nuclear furnace, all right? So the nuclear potential energy is actually getting converted into heat and light. So during the nuclear reaction of fusion, it brings a ton of heat, a ton of light, and then that energy reaches us. But how did the sun's energy get, where did the sun get this initial energy from? Well, the sun initially got it from, back when it was formed, gravitational potential energy. All the gases and dust that was in the proto development stage of our solar system, before the sun existed, there was just a bunch of gases and stuff. Well, gravity caused all those gases to move towards each other. And when those gases started moving towards each other, they started colliding with each other and building up heat, and the gravity created pressure. And eventually the heat and the pressure got so high, it started a nuclear reaction. That nuclear reaction generated a huge amount of thermal energy, which still does today. And then that thermal energy gets radiated to us. And then that radiant energy makes it to the surface of the earth, where the plants take that sunlight and use photosynthesis to make chemical potential energy that we call glucose. And we eat that potential energy, and then we actually can do our day-to-day business, such as moving around. So we consume that chemical energy that helps us move our bodies, so on and so forth. So that's how energy gets transferred all the way along. Now, eventually that energy has to go away. What form does it eventually go into? It goes into what's called latent heat, which is just a low-level heat that ends up scooching off out into the cosmos, that leaves the planet. So, and here is the more detailed explanation of what I just said. Now, here's the other thing. Energy losses and heat. Okay, energy is actually never really lost, so to speak. It just transfers from one spot to another. But here's the thing. During every transaction, some of that energy is lost. Some of that energy is lost into the form of useless heat that we can't use later. So consider this like transaction fees. Every time you have a transaction, there's a fee that removes some of your money away from you. Same thing happens. Every time there's an energy transfer, there are losses. So for example, in a car, most of the losses are in the form of heat. You also have losses in the form of sound because we can actually hear the car doing its thing. Now, for us living on Earth, we're getting a lot of energy from the sun. And believe it or not, most of the sun's energy is just radiated away to other parts of the universe. This is actually important because if the Earth actually absorbed all the energy thrown at us by the sun, you wouldn't be able to live here, right? It would be too hot because the sun is just too darn powerful. So the Earth dissipates energy at approximately the same rate as we absorb it. Well, thanks to global warming, it's actually the rate of getting rid of it is now slower because we basically surrounded the planet in a nice big, carbon dioxide blankie, which is preventing the Earth from cooling down at the rate that it's supposed to, which is going to have some long-term environmental impacts. Next concept, conservation of energy. Energy can't be created or destroyed. It can only be go from one form, transferred from one form to another. All right, I have to change that little grammar there. So the total energy before must equal the total energy after. And that's what this says. The total energy before equals the total energy after. So we're going to talk a little bit more on this later. But again, anytime there is a change of an energy transfer, the overall amount of energy stays the same. So I did mention work. Well, work as in going to your place of employment. But in physics, work means something different. Work is defined as a force through a displacement. Now, according to this definition, work is only done if the force acting on the object is in the direct line with the motion of the object. Let's go back to our example up here. Let's bring it back down. All right, so here we got our little block. So right now, it's sitting on the ground and it isn't doing too much until we apply an upward force. So we apply, let's call this the force of the lift. All right. So now when we have this lift force, we raise this object up. Well, what we have done is we have applied that force through a displacement. So if you look, the force and the displacement, they're in the same line. They're parallel to each other. So this formula says that if we apply a force in the same direction as we move, we are doing work, which is the product of these two numbers, the force times the distance. Now, what happens if we lower the same object here? So what happens when we drop this thing? Well, now when we drop it like this, we're still applying a force up, but now the displacement that we had went from being positive to negative. So the force is positive, the displacement is negative, and when you multiply a positive and negative, you get a negative number. And that means that we got negative work done. What the heck is negative work? Negative work means that we just took energy out of this. So by bringing this box back down, we actually took the gravitational potential energy that we had and removed it and put it in a different form. Where does it go? Into U. Into what form? Heat. That's why when you work out, it gets so hot. So for work to be done, the force and the displacement got to be in the same line. So if you take a look in this case, if we're lifting an object but only moving it laterally, that's a 90-degree angle. No work is being done. And that means this. If I move this object to the right, it's not going to hit the ground any harder than if I left it here, right? So by moving it in this direction or by moving in that direction over there, there'll be no change. There'll be no change in the amount of energy in this block. I mean, sure, you're applying it, you're using up energy to do this job, but the object itself isn't going to hit the ground any harder by moving it to the left or to the right. Only way we can change the energy of the block is by raising it higher or lower. So that's why in this example here, the force and the displacement were 90 degrees to each other, no work was done. But here, when we push in the same direction as our displacement, work is being done. And what happens is when you do that with an object like a cart, the cart will start to accelerate. So let's take a look at some examples of the formula here. So we have a 5 kilogram sled and we're applying a force of 15 newtons. All right. And we want to figure out how much work is done if the sled moves 15 meters and if it moves 10 meters. All right. Well, if it moves 15 meters, we take our force, which is 15 times that 5. That's 75 joules of energy. But if we go 10 meters, I see my mistake here. That's supposed to say 5 meters. If we go 10 meters, the amount of energy is double, which is 150 joules. All right, so some more formulas. Gravitational potential energy. So to calculate the gravitational potential energy, we use the following formula. EG stands for the gravitational potential energy. E stands for energy, G stands for gravitational. M is the mass of the object, G is the acceleration due to gravity on Earth, which is 9.8, and H is the height above the ground. So if you want to figure out how much energy with respect to gravity something has, you need to know its mass, you got to multiply that by 9.8, and its height. So the factors that affect it is the heavier it is, the more energy you have. The higher it is, the more energy that you have. So this is your gravitational potential energy at a specific spot above the Earth's surface. All right. So what happens when we change our height? Well, when an object is raised, it gains gravitational potential energy. When it is lowered, it loses gravitational potential energy. So when there's a change in energy, work is being done. So a change in gravitational energy equals work. So work equals a change in gravitational potential energy, and the formula for the change in gravitational potential energy is mass times G times delta H. And if you recall, delta H is your H2 minus your H1. So let's take a look at a couple of examples. How much energy is required to raise a 30 kilogram object to a height of 10 meters? All right. Well, mg delta H, that's our work formula here. Work due to gravity. So delta H is our H2 minus H1, 30 kilograms times 9.8 times 10 minus 0, because that's your final height. This up here, that's your H2, and this there is your H1. And that works out to 2,940 joules. Now, example 2, how much energy is required to lower a 30 kilogram object from a height of 40 meters to a height of 15? So in this case, our mass is 30, gravity is 9.8. Our final height is 15 meters, and our initial height was 40 meters. So that was our H2, and this is our H1. Now we get a negative number. And that negative number is okay. It just means that we've taken gravitational potential energy out of the system and put it elsewhere. So if you are carrying it down, it's going into you in the form of heat. That's why you start busting a sweat. Or if you drop it, it turns into bulk kinetic energy, and then when it hits the ground, it turns into sound and permanent deformation and all that fun stuff. Next, kinetic energy. The concept of kinetic energy is, again, the energy associated with motion. And this is specifically bulk kinetic energy. So this is energy kinetic is equal to 1/2 m, which stands for the mass, and v, which stands for the speed of the object squared. Now, the key thing is the speed has to be in meters per second, and the mass has to be in kilograms for this to work. And the energy is measured in joules. So let's take a look at a couple of examples. We have a 50 kilogram mass, and we want to figure out how much kinetic energy at 50 kilogram mass if it's traveling at some specific speeds. So the 50 kilogram mass, if it's not moving, well, it doesn't have any kinetic energy because it's not moving at all. So anything times 0 is 0. So we're at a standstill. If the object is moving at 2 meters per second, so it's going to be 1/2 times 50 times 2 meters, 100 joules of energy. At 4 meters per second, that's 1/2 times 50 times 4 squared. That works out to 400 joules. So if you notice, a doubling of the speed actually works out to a quadrupling of the energy. And the final formula for today is spring potential energy. Now, the formula for the spring potential energy is very similar to the kinetic energy. ES stands for the energy of a spring. It is equal to 1/2 times K, And K is something called the force constant of the spring, or basically K represents how stiff the spring is. The larger the K value, the more stiff the spring. The smaller the K value, the less stiff the spring is. And X represents the distance that you either compress the spring from its natural state or the additional stretch. So that's also so it's either the amount of compression or the stretch, which is also known as the extension. So if you're compressing it, negative number. If you're extending it, it's a positive number. Doesn't really make a difference though, because when you square it, it makes a positive anyway. So this is the energy associated with a spring. So let's do an example. Determine the amount of energy stored in a spring with a spring constant of 100 newtons per meter, which means that for every meter you compress or extend a spring, you get 100 newtons of force out. So with 2 meters, you get 200 newtons. 3 meters, you get 300 newtons, so on and so forth. So if it is compressed a total of 20 centimeters, all right, we want to figure out how much energy there is. Well, that's going to be 1/2 K times that. K shouldn't be there. So 1/2 times 100 times negative 0.2. When you square it, it gets rid of the negative, and we end up getting 2 joules. If we extend it by 10 centimeters, we get 0.5 joules. And that should be a negative. No, extended. I got it right. Sorry. That's negative because it's compressed. That's positive because it's extended. So notice, this is half as long, but the energy is a quarter. Okay. Well, that's it for now. Next video lesson, I will go through these sample problems.